and then that's when I got into the Scala stuff, So I've only been doing Scala for 2 weeks, But again, it's pretty exciting. But yeah, so there's other people I think who want to do stuff, but yeah, sometimes they drop off. Now that was a Sunday class. Some people have family, kids and all that, which was an opportunity to get away, and in some ways they couldn't get away.
So, sorry.
Hi, how you doing?
Lovely.
My name is Ilya. How's it going?
Nice to meet you. And I guess quick introductions.
Ilya, I work for a fitness level setup.
I'm done, so I just work for self right now, but was working at Sony.
Hi, I'm Angela. Graduate in college. We'll be starting work soon, next week.
I actually work for a privacy company. I'm Rohit. I work for a startup.
Thanks for the introduction again. My name is Avneet. I currently work for Microsoft and been doing machine learning for a few years. And obviously, I always feel the need to learn more and learn deeper. And one of the best ways of learning is that I found is if you actually try and teach what you're learning, then you end up learning a little bit better. So that was sort of a very selfish motivation behind this. Thanks. So I picked this course. So normally, the way I end up studying is if there are certain people who are really good at certain algorithms, like for boosted decision trees, there's a guy who created those algorithms. He has a course. For SVM, there's a professor in the UK. He has a very good talk on that. So that's how we're learning it, which has been bits and pieces here and there. But this is one course which sort of ties up a lot of concepts and a lot of algorithms together. And I'm pretty much going to go through exactly what he's gone through. So anytime you like, you can just watch his YouTube videos. This guy is a physics professor, and he sort of explains most of these things in a very simple, intuitive manner. So you can actually go very deep into the algorithm so you can understand what's going on. At the same time, he keeps it simple enough so it's easy for anyone to understand. So I've just taken snapshots of his videos, just saves time. And I'm going to try and go through these. If there's too rudimentary and you already know most of it, we can go faster. If you need me to slow down, just feel free to stop me like we do. So today, actually, we will be talking about one algorithm, which is known as nearest neighbor algorithm. It's also used for other things, like Rohit was talking about anomaly detection. So nearest neighbor algorithms can be used for anomaly detection. And I remember during the thing, I'll bring that up. So one of the things that's useful for is classification. And to try and understand what we do in classification is we basically have a set of x and y's. The y's are our label, x are our features. So what that would mean is, let's say you go to a bank officer, and a bank officer is trying to figure out whether he or she wants to give you a loan or not. So an algorithm would basically have, if you can imagine in any spreadsheet, let's say Excel, one row which has your name and your profession, how much you make, where you live, what your degree is, anything that's pertinent in figuring out whether about your capabilities of returning back that loan. And one label would be, will this person return this loan or not? So that's a 0 or 1 answer. If it says yes, you'll probably return the loan, then the bank office will probably give you the loan. If it says, well, you won't return the loan, the bank office will probably won't give you the loan. So what you're trying to do is you're trying to figure out this label of 0 and 1. So trying to classify your data into two possible groups. That doesn't always have to be two groups. This one just happens to be binary classification. But most of the work ends up being binary classification. That's the most popular one. And in order to figure out which of those classes to put you in, whether 0 or 1, there will be a bunch of features which we just talked about. Your income, how much money you're already paying in different markets and things like that. And your education. So what basically happens is that there is a data set in the past which the algorithm already has seen, where it knows for different other people how much money they were making, how much money they owe in different loans, how much they were paying back every month, what was their education. So it has a lot of information. It also has information whether that person paid back the loan. So the algorithm's task is to look at the past data where it has these labels, and based on these features try and figure out these labels for cases where it doesn't really know. So if a new customer comes in, they don't really know if that customer will pay back the loan. So that's essentially what they're trying to do in binary classification. Yeah, so essentially what's wanted is good predictions from the observation. So one of the key things is, so here it's very difficult to see on the screen, it's slightly better. But these are dots of two different colors, I think they're red and green. And on x-axis you have one feature, on y-axis you have one feature. So let's say the x-axis has your height, the y-axis has your weight, and they're trying to predict if you'll be able to pay off the loan or not. That doesn't seem very good predictors of what you're trying to predict. Hopefully our height and weight don't really tell you if you can pay a loan or not. So you basically see there's a whole cloud. There is no easy way of partitioning this data based on these two features and trying to say whether you can predict if somebody's going to pay a loan. So if you don't have good features, then your classifier really cannot do much. So now we look at the algorithm of n nearest neighbors. So this is a very simple algorithm. So here we have two different classes. We have these dots and we have these plus signs. So these are two different labels, and here we already know for these points what the labels are. But now our task is, if I have a new point, let's say here, then how do I figure out what label it should be given? So that's the question. So any guesses based on just the name of the algorithm? What is one thing that we can do here? Right. So the simplest thing is to look at the neighbors. And the starting point is look at the nearest neighbor. So let's say a point is here. The way it's been broken up, they've tried to break the boundaries around each neighbor data point. So if it's here, then the nearest neighbor seems to be this guy. And so it's really that simple. You find who the nearest neighbor is and look at the label for that nearest neighbor and just use that. Any questions around that? point will actually go into the idea. So there's a modification of nearest neighbors, and that touches the ideal support vectors. So in some sense, yeah, I mean, at the end of the day, anything that's following this boundary, anything below that is going to be one label, anything above that is one label. So essentially you can separate them with a line. So in that sense, yes, an SVM could pretty much do the same job.
How are the boundaries defined? Like how do they come up with the boundary?
So frankly, I don't know how they came up with this. I can understand the idea behind it. So this line is sort of saying anything below this is going to be closer to this point than any other point in its neighborhood. So this guy, if a point is here, the distance between these two guys is larger than these two guys. So that's what they're trying to get into. How they actually get that, I don't know. That's a good question.
The point can be physically closer to the other point, but it was similar to the point where it originated.
So the point, well, if it is physically closer to this guy, please, yeah.
So let's say there's a point right over here, and this point is closer physically to this point is probably closer to this point. But because it's still in this neighborhood, this point is going to put on the
So ideally, if the algorithm did a job right, then if a point here was closer to them here, it should have cut the line here. So if it is not doing that, this algorithm is doing its job wrong. So if any point, so essentially just like you said, whatever labeled point is closest to a new kind point will give it the label. So if a new point comes here, the nearest point is this guy. That will give the label. If a new point comes here, the nearest neighbor by definition ends up being this guy. If this guy is not the nearest neighbor, and this guy is the nearest neighbor, then there's some problem with the algorithm. The task of the algorithm is first find the nearest neighbor. Second, whatever label is being given to the nearest neighbor, give it this label. Okay? So this is one of the concepts that I actually heard about it 8-9 years ago. I never really understood it. And for the first time I went to the accepted it. At least in a way that makes sense to me. So this is very similar to an idea of underfitting and overfitting. Have you guys heard about that? Okay. So essentially bias and variance is the same thing as underfitting and overfitting. And this algorithm has a problem. So the one nearest neighbor is good at one of these and very bad at one of these. Can you guess which one? So amongst bias and variance,
Variance system.
variance is good, meaning is it high or is it low? That's correct.
That's because they see that only one neighbor in the neighborhood.
Okay.
So that is would be high and vice would be low.
Okay. Let me first give the definition that was given in the course. So the definition of variance is if you have a population of data and you take a sample from that population and you build a model on that data, you have a certain model from that. Now you take another sample from the same data and you build another model, you have another model. So you can do that a bunch of times. Now, if these models vary a lot from each other, that means there's a lot of variance.
That's a result.
Right. So, in this case, with the variance we have, if you keep, what will happen if you make another model? You have, let's go back to the previous slide. So you have a model based on all these data points. Let's say now you only have half of them randomly selected. Will your model change or not?
Are you randomly picking?
Right.
If you have large enough ones,
Convergence becomes a, what things converge.
I mean, if you take, let's say we pick this point, and this point, and this point, and this point. Now the decision boundary is sort of moving these guys. When you take away these points, the decision boundary will move here. So if you remove some points here, right, it is going to overfit the data because all it's looking at is whatever is the closest point. So in each area, the closest point is telling you what the label will be. If you remove that closest point, your whole model is changed in that area. So the variance is very high. And the bias basically means if you keep resampling the data and you create new models from that data, and you sort of take an average of that. So maybe 10 times you resample this data, and 10 times you create new models, you have predictions from that. And you take an average of that. How far away is it from the perfect model, which really knows how to separate the two? That is sort of the idea of that. So a simple example would be, so it's essentially like overfitting analysis. So you have two features, X and Y. Let's say one is height, and the other is width. And your data is like this. And suppose all that you can do is make a linear classifier. Sorry, a linear regression. So the true model would actually should look more like this. But because your model can only make straight lines, the best it can do is it can make something like this, something like this, something like this. The average basically would go to here. This would sort of be an average line. So it doesn't really have, the model doesn't really have the capacity to fit these things. So this is underfit. So you always have a bias from the perfect. Now these guys, this has a lot of capacity because every labeled data point allows you to change the prediction of the model. It can really curve around all over the space. The smaller the space, you really funky linear models all over the place. So it has a lot of capacity to move around data points, as opposed to a simple linear line which will just come from here.
Can I mention like a real world example of like, at least in terms of the S&P 500, the stock market, there's what's called volatility instruments, the VIX, which are futures contracts. So now I'll go back a step. There's a fixed spot price. In other words, even though there's S&P 500, you have options for S&P 500 that are being sold and bought. So there's a volatility that's measured from that. not historical volatility, it's cloud, by how these options are being priced and differences and so forth. So, that's called like the implied volatility, so there's these VIX futures contracts that trade, towards the point where every month they expire these contracts. So you'll have a term structure that's like 9 to 12 months out, and every month there's a contract expire, the middle of the month. So the thing is, eventually these contracts have to converge towards the spot price. The spot price being what's priced on the real options. Right? These are derivatives. So they talk more about, even though these are volatility instruments, they talk about them as being like variance swaps. So when I hear about variance and then convergence, how would you talk about with any of this, like even how maybe nearest neighborhood help or so, where the term structures, have to go to a spot price and converge, but they last up to 9 or 12 months, the contract. Did you see nearest neighbor helping that?
So nearest neighbors
It's
is,
legit, linear regression, like you said.
so nearest neighbors is used in predicting stocks. And it's slightly different. I don't know if we can map the variance in the futures directly to what we're talking here. But in terms of using nearest neighbors, essentially what they do is they look for, here you can see these data points, these are two-dimensional features, but it can be a 100-dimensional data point. So one of those points could be Microsoft, the other one could be IBM. So if historically you have seen that IBM and Microsoft move similar, then you can treat them as nearest neighbors. And if you see, let's say 5 of these together, they are very close neighbors to each other. 4 of them, the stock has just moved up, the 5th one hasn't. And there's a high probability the 5th one will also fall eventually. So you can put your money on it. Don't take my word for it. But that's one of the things that we can do. Also, you should have made money on it.
I have a question. Yeah. I was before you mentioned the last point, like, how do we have to first know, right? It's time consuming and very right? I guess. So we have to know which is good and which is bad to come up with points on this diagram first. I just want to confirm.
Correct.
And we have to rely on whether the data that we have was correct.
Correct. So the problem we are working with is anomaly detection. Now, k-nearest neighbor also helps with anomaly detection. Not exactly this one. So there's some of the right way of doing anomaly detection, and there's the easy way of doing anomaly detection, which is also extremely efficient. And one of the big corporations in the world that I'm aware of actually uses that. So you can actually go into the past and find out what were anomalies, label them as anomalies, and all the other data as non-anomalies. And then you can try and predict. So that will completely work here. But the problem with that is all you will get is past patterns. You won't get any new pattern. So anything that has happened in the past, you'll be able to catch it in the future. But if you haven't seen that in the past, you won't catch it in the future. And nearest neighbor actually helps you find that comes out of the method where you don't need past patterns. So essentially, one of the things that nearest neighbor does, this is a very different lecture altogether, is let's say you have a point here. Now you look at all these guys, rather let's not even go there. Let's look at these guys. So if you look at all these points here, they are very close to each other. Right? The distance, average distance of these points with each other is very little. The distance, average distance of this guy with all these points is very large. So if you just take the ratio of this distance, these distances, and you sort all the data point by that, then the guys at the top have a high probability of being anomalies.
there is room for, let's say tomorrow we have more to add a new feature. Is this algorithm is there a way to introduce like new feature on the fly, or do you have to change everything? Because all the other points will change.
So we will have like one more plot of
Right.
positives and negatives.
Okay.
But the variables remain same.
So the difference will move around. That's what I mean.
No, and you will have, I mean, you know the rights and the blues. Irrespective of whatever features you want to have in it. You know what they are. Now you are saying I have a new feature X. Fine. Let that be, but the label will still remain same.
Label is same, but the points location will change around.
No, so you have a K, you have usually had 3 dimensions, now you have a K plus 1 dimension. So what happens is you going 3D to that. Right, so you need to get those labels for this feature value from all the different points, just not from all the points.
Okay, so we okay.
So let's say you have just 2 dimensional and you have 3 plot, now you have K plus 1, third feature. If you just ignore that, you would still have this plot.
Yeah.
So now it will be a straight line here, and once you have to find one, it will probably appear plane, but that's like a different thing.
Just imagine this is your x and y axis, and now you have another feature that's coming out here. So some points will be higher, some points will be lower. But if you remove that plane, you're back to this point. So yes, you can absolutely add new features. And that's really what we end up doing most of the time, and we keep adding new features.
So one takeaway from this, every point my word is, since you have a very, since you can make a very non-linear different boundary,
Right.
you have more degrees of freedom, so to speak. So you have more parameters, so to speak, and hence you have higher bias.
I agree.
I agree, that's what I'm trying to agree, like, and more bias.
So now, in order to, these parts not very useful, but in general, in order to increase the, in order to decrease the variance, one very simple way is that instead of taking one nearest neighbor, you sort of take more than one. So let's say 5 nearest neighbors. So one of the places where nearest neighbor algorithms work very well is predicting property prices. So the real estate agent will talk about comps. So essentially all they are doing is they're looking at comparables. They're looking at other data points which are very similar. So you find other houses that are very similar to this house you're trying to predict the value for. And then you sort of take an average of that and then you predict the price. That's a regression model. It's the same idea. And so suppose, I saw this very interesting case. I was looking at this data a long time ago, where all the properties were at a very good price, a couple of hundreds of thousands. Then there was this one property which was sold at $47,000. And I was very curious. I looked into the data and I realized it was sold by the same person to the same person. But the guy sort of had a company which owned the house and something like that. So if that had been your one point, then it would give you a very long prediction. But now if you have that point and 10 other points, and you take the average, now it's sort of a better prediction, and the variance now decreases. That gives it a little bit more stability to the model. So that increases the variance, but of course it decreases the bias. It doesn't give you as much flexibility anymore of making all those curves around the points. So let's say this is one space for all the houses where the mortgage will be paid out. This is all the houses where it won't be paid out. So this is, let's assume, somehow we know these are the right models. So now we have gone from, instead of looking at one nearest neighbor, we're basically looking at multiple nearest neighbors. If we try to predict upon here, what we'll do is we look at multiple points in the neighborhood and end up giving the prediction of this guy. direct prediction system. So when we increase the number of nearest neighbors, the good thing is the variance goes down. The model is not as big as it used to be, but it loses its capacity to take this very fine edges and points. That's one of the trade-offs. And which one is working well for you is something you have to play with your data and figure out. And we've talked about that. So it talks about some of the points of nearest neighbors. One thing is very simple to understand, and if the number of dimensions are low, then you can actually move pretty fast. If the number of dimensions go high, then it becomes difficult because now you're computing the distance of one data point with another data point. If that other data point has 1,000 features, now you have to look at all those 1,000 features to figure out the distance of these two data points. But if it had only 2 features, then you can do that very quickly. So if the number of dimensions are low, you can actually move very fast. It's a lazy strategy. So essentially, during training, you're actually doing nothing. You don't have to do anything during training. Right? For all practical purposes, that really happens when you're trying to predict. So when you have a new data point, that is when you try and figure out which is my nearest neighbor. But during training, you don't have to do anything. It's a very lazy strategy. During training, you do nothing. All the work happens during testing. Yeah. Right. Very important for us. So the whole idea is that we have some data that is fed into the model, where we know the labels. So we know these houses the rows are paid off, these houses the rows are not paid off. We already have those answers. And we have some understanding of what about those houses, like how expensive were those houses, how big were those houses, what was the neighborhood of those houses, and things like that. So that is something that we already know. So this is something we train on. So the model is going to look at this data and learn something from this data. Let's say it's because if this is a particular neighborhood, the probability of the known big data is there. So now the model has learned something. So it took some training data and the model learned something from the training data. And now you give it some data where the model hasn't seen the labels. The model doesn't know whether this house is fully paid off. That would be a test data. Where as a user, as somebody who's training the model knows what the label is, but the model hasn't yet seen this data. So first you look at the training data and you learn things about the data to be able to predict the labels. And second time around, actually testing it. Does that make sense? So,
But when you say you don't have to do anything for the training, you do have to build the model, right?
in pretty much every other case, yes. This is an unusual case where you don't have to. Because the way you run this model, the way you run predictions. So typically what will happen, let's say you have a regression model here, right? You see this data, you build this line, and now you forget the data. All you need to know is this line, right? And you have a new point that is here, and you're trying to predict this guy. You basically say, if this point would be on this line, what would be the value here? So this model is completely separate from the data now. It has learned whatever it is. That's not what's happening here. We actually go back to each data point to predict anything. Sure. So this is your data. You haven't done any modeling on this. This data is just the data. Now you're trying to predict something. Let's say a new data point comes here. Now what you have to do when a new data point comes here is you find the distance of this data point with all the data points it here. And this you do at prediction time. And then from all those points, you find which is the closest one to the data point for which you want to predict. When you find the closest, you give it that label. So nothing happened during training. Everything happened during prediction.
But I thought the boundaries we draw during training. We could draw the boundaries during training, and then for making prediction, we could only check like when on what boundary it lies.
Yeah, so that would be a variation on this algorithm.
Okay, it's more like a human.
Absolutely.
I think it's right. Basically, like drawing boundaries for testing, whatever is just not human. That's just the algorithm is just making you want to make it happen.
So the interesting thing is, in terms of training set, if you look at what's the error in the training set, the error is 0. It's a perfect predictor as long as the points don't overlap with each other. So this is a very important point because training error means absolutely nothing unless you have testing error. So here, if you want to make a prediction for this point, it's very simple. You find this point, you already have a prediction for that. You will have the right prediction. You will never make a mistake for the points which already existed because you know the labels. So the training data error is always 0. But when you make actual predictions, then you will make mistakes. So your test error won't be 0, most likely. So yeah, that's basically all the things.
What happens if the training data is like improperly calculated or done?
If the labels are wrong, there is nothing the algorithm can do. So one of the first things they teach in statistics and same applies in machine learning is garbage in, garbage out. So the quality of your model can never be better than the quality of the data. So the labels are wrong, and that's clearly an issue. And that happens in real time all the time.
I kind of not agree because maybe I'm not sure. Because the whole point is you initially you have less data. Okay, and then over time you have more data, and that's when your model improves and your predictions get better. Right? So initially with the small data you could be completely wrong. Let's say you could be like maybe 50-50 wrong. That's fine. You could be like reversing it. But over time you're getting accurate, maybe like 99% accurate. So what do you want to say with that? Because initially your training data was wrong. You can say that.
If it's a data coming in this 99% accurate or 1% wrong, right? So it could be like one nearest neighbor to the other, right? In that random chance, it still finds the wrong answer. So if you say 7 nearest neighbors, and your one data sample happens to be wrong, that's the other 6% likely to be correct. You still make that prediction. But what you're saying is you notice that like this span of this long-term data is coming in, right? If your training data is like 50% chance of being correct or wrong, that's too much. Right, the assumption that you is that training data is coming in this way, like 90% accurate, so then your model can try to be 90% accurate. If your model training
do a few runs of the data to find out how wrong you were at various points, and maybe feed that as a feature, at least to improve your prediction in the future. Not maybe to make them, 100% accurate, but maybe make that additional little improvement. Because every like 5% or so improvement could make a difference, right? I mean, but you're saying though at one point that less features things run faster. I mean, does that mean that like it may become more practical to do this more in real time, like nearest neighbor? I mean, how many? I mean, it's all relative too, right? How many? Like it depends on the system you're running. Yeah, supercomputer versus laptop. But is there anything really preventing people from running? I mean, because you talk about like giving it the training data, and classifying it and such. And how often would you like house it with real estate? Any idea what you could say about how often they would basically run or like predicting loans? If let's say a real company, I don't want to get off the theoretical.
I know one real company, I should name them, but I asked them this question: how often do you train your models? And they're on Amazon Cloud, and they basically run it every day. What they've done is they have a different model for each city, and every night automatically those models are running, and they get new predictions.
My understanding, like at H2O, like for Cisco systems, I'm pretty certain they mentioned that Cisco is running into tens of thousands of, or they're running the models through tens of thousands of times a week or so. Or still their sales and currency change, although they sell their stuff in US dollars. But
basically it's like it's an active it's a daily run. So as you keep interacting, you keep on changing the waves. So it's not so these waves are not static in that. All I need is I remember I worked in government, they use reinforcement learning for some.
yeah, I mean, is that the thing is that we still wouldn't say that machine learning is reinforcement learning? It's part of it, but I mean, just in the sense that we're talking about nearest neighbor, we're not necessarily talking for all the way about reinforcement learning, no.
So reinforcement learning, I don't think it has to be an online learning. Reinforcement learning could still be done like offline. Yeah. So what the learning is like online learning. But you get a function integrated to the model like that or something. So why did it like more like that? Yes.
You would be doing it, yes, still effectively, well, okay, yeah, you would still be making predictions real time now on loans, even if you run it overnight, let's just say. Yeah, what would be the point of running it maybe with loans like during the middle of the day several times? Maybe on the stock market could be different, right?
So in terms of houses, they basically get new data about houses being sold. So that helps them. So if there's a new house in a certain neighborhood which was recently sold, then it improves the prediction of all the houses in the neighborhood. So each day it will make it a little bit better. As it gets more stale, so one house was sold more than 3 months ago, now the price of that and what's going to sell today is going to be different because the market is more some points away.
And that's the thing, so when you're talking about like the more recent data is probably more relevant than, I mean, is it relevant to look at data on housing from the 1950s? It's probably not as relevant to what Silicon Valley is, although you could in some ways look at it, but still, does that mean anything with regards to what we're still talking about bias? Or not, no, right? Because we're talking about that we're not also giving weights. I mean, well, we don't have to give any of the data any sort of weight, right? To say that more recent data is more relevant than past data, right? I mean, like, if we have data from, let's say, the last 20 years, we don't have to say that the last 5 years is more relevant than the first 20 years.
You can put an example, like let's say you
trade the stock market daily, or I guess it wouldn't matter why. I'm trying to say trade the stock market daily when I can run the stock market. Somebody could hold it longer, but obviously there's like stochastic indicators, relative strength indicators. There is linear regression, but you can feed these also to those features. I guess that's what you're talking about, at least, with regards to. Well, yeah, I was mentioning.
Next slide.
Yeah, let's do that.
Okay, thanks. So, one of the things that happens in nearest neighbor is every time you get a new point, you basically compare its distance with all the points you find. So, if there are 100 million homes in the US, and you actually try and go through all these 100 million homes, then basically takes around 10. Now, one of the things we want to do is we try to speed up this algorithm. And in order to speed up the algorithm, there are a couple of things we can do. So one example the professor gave is basically he created a for loop where you have some endpoints for which you want predictions and some endpoints for which you already have previous labels. Now for each of those endpoints, you're going to find the distances with all of these endpoints. So it's n by n matrix, and he basically runs the entire for loop and fills up all the points in the matrix to find out the distance between each point for which you want prediction against all the points that have already been predicted. So one of the simple things that we can do is for the distance of any point n with m is the same distance with n with n. So you're putting two numbers in the matrix. Your matrix is essentially a mirror by the diagonal. So instead of filling all the matrix, you fill half the matrix. So you don't have to fill the entire matrix and just fill half of it. That's sort of one way of speeding things up. The other thing he mentioned is you can basically convert that whole thing into simple algebra, which he shows here. So these are the endpoints and these are the endpoints. Let's say these are the ones you can predict. They all have p feature values. So now you want to create a distance matrix. So he has this equation over there, he breaks it up, it becomes these simple things. And what happens is something like MATLAB, which has everything in matrices and vectors. It has a lot of subroutines. So while the for loop took 3 seconds, putting this in simple algebra takes 100 times less, 0.03 seconds. So this is one of the ways you can actually speed up. And the other way he talks about is this. So let's say all your data points exist in 2 features. Let's say it's height and weight. And what you do is you try and build a KD tree around it. So you don't have to go through all the data points, but only a subsection of data points. So let's say these are your data points on this region. So it's difficult to see right now, but there are these data points laid over here. And you find a place where you want, and these are the 2 axes. You find a place on this axis where you want to place this. Now there are multiple ways of doing that. You can take the mean or you can take the median. Simple ways to take the median, because if you have outliers, then it can actually impact the mean. And median is insensitive to outliers. So let's say you pick this as your median. So everything left of here is one thing, everything right of here is one thing. So once
How do you decide whether the median around this dimension other than this dimension?
in this case, he basically looks at where is the variation more. So he saw more variation on this dimension, less on the other. So that's why we went to this. But yeah, that's a design question. We can figure out what works for you. So we basically divide that into 2, and after that we divide them on this side over here and on this side over here. So you broke this up into different spaces. a new data point comes in, let's say this is the new data point. So now for this guy, we know the value of these two features. So we come here and we know this guy is greater than this value. So we're only going to look here and not going to look there. And then we come here and we see this partition and we say this guy is greater than this partition. So we're only going to look here and not here. Now again we see this guy is less than this partition. So this is the area we're going to focus on. So now instead of looking at all these data points, we are only going to consider data points in this region. That reduces the number of data points you're going to look for. Now, of course, that has issues. Now, the basic issue comes from the fact that whenever you're trying to figure out a distance, essentially it's a radius. It's a circle in 3 dimensions, a sphere. And whenever you're partitioning each feature, you're cutting it by a line. So you're creating linear spaces and you're trying to figure out spheres in them. The problem is the spheres will cut through these lines. So in this part, it can be possible that your closest point is this guy. And you make a circle around this point. And you realize that, well, there's a guy on the other side of the boundary which is closer. So now, even though ideally you would have wanted to just stay here, I actually also have to come back here. And then you notice that there might be a point in this side also, and you also have to come here. So there are times when this algorithm will work, break into small pieces, and there are times where it won't. So whenever you find, so the procedure is you find the closest, and you take this circle, and if you find it cutting over, then you have to sort of backtrack. So the whole thing, this thing can be seen as a tree here. So you come to this guy and it says it's on the right hand side. So you came here, this side. And over here it goes to the left hand side and you came here. So you have to that. And then again it goes to the left. So this graph basically shows how you traveled in this space. But now because you also have to come back here, you sort of backtrack again. So in some cases it will work. So if you find, let's say the point was here, your new point, and your nearest neighbors, you look at the nearest neighbors, this guy and this guy, and then you create a radius around here, it doesn't cut any line, you're done. Then you don't have to look at any other thing. This was just an example to show that this thing can go bad, and you can end up looking at a lot of data points. But in a lot of cases, you will actually find points nearby that won't cut any lines. And this really speeds up the whole algorithm. Now, the other thing it says is, again, the good news is in low dimension networks are fine. In higher dimension, the hyperspheres that you're going to create, the probability of them cutting through the lines is much higher. So then you have to backtrack a lot and you have to work hard again. The whole algorithm works much better in low dimensions than high dimensions. Now another solution that they have, the problem we were having was we find a space which has closest neighbors to our new point, and that was having some problems because the spheres were cut out. So here what they do is they do spill trees. So you have the original line cutting up here, but then instead of saying everything to this side is what I'm going to look at, you go a little bit on the left and say everything to this side is what I'm going to look at. So previously what we had was we had just one line in the center, right? And when you were going through the tree, you came to this point and you said, oh, my data is going to be to this side. So I'm only going to look at the data of this side. I'm going to forget the data on the other side. That's what we've done in the previous one. Here what happens is, we come here, we find our data, we see that this line is separating it. We're only going to look on this side, but instead of saying we're only going to look at this side, it says, well, actually, I'm going to go a little bit to the left. I'm going to look at everything on this side. And what that does is that if this was your point, which you were trying to predict, and this was the nearest neighbor, you could have made a circle around here, and that would have cut this line, and I would have to look at all these points and all these points. But now, that thing is going to be on the right of this line. So it's sort of spilling the tree a little bit. So then, instead of looking at just these points, you will always look at these points, which increases the work a little bit, because now you have some more data points to look at. But what it does is it decreases the cutting of the lines by this field.
So just to see the point is that falling on the band actually put on the both left and right side. I see. So you actually have to like do less of like backtracking because you can nicely find the metric of that point is like all on one side of it.
Correct. So it reduces the chance of backtracking because the circle will still be on this side. But then it increases the work because now you're looking at these functions. So, and then you mentioned that in reality what people do is sort of hybrid of split trees, where they will take one dimension and they'll do a split tree, on the other dimension they'll do a chest tree, then the next part will be a split tree. But all these are basically meant to speed up your process of finding the nearest neighbors. So the summary is it's a decent classifier, but can be slow. And there was an interesting study I saw a long time ago. So for each problem, most of the time, there's a certain algorithm that works best for that problem. Now in practice, we may not always, I think we have a tendency of having a favorite algorithm. We use that. Some people love neural networks, some people love boost decision trees, some people love SVMs. So people love their own algorithms they're fond of. But if you actually try all of them, then different kinds of problems have different kinds of algorithms solve them best. Like, I think predicting house prices, something like nearest neighbor works out good, because it's sort of intuitive. That's what people have been using for so long. You find a similar house, and your prices will be the same. So in some cases, it will work as a very decent classifier. But if you have a lot of data points, you have to find a distance with all those points, and they have a lot of dimensions. You're using Euclidean distance, so now you're taking squares on both sides and adding them up. So the number of features go high, your computation goes high. The other thing is you can change your similarity measure. So the various ways of defining distance between 2 points. There's Euclidean distance, there's Manhattan distance, and so on. So by choosing that, you change how your algorithm performs. The other thing is a very simple thing. Now, if you have a feature that says the area of a house, now you can have it in millimeters, you can have it in centimeters, you can have it in meters, you can have it in feet, even in miles. That will impact the distance in terms of the measures. So something says, 1 million millimeters versus 100 meters. So the 1 million versus 2 million will be a huge number. So by changing how you measure your feature, you will impact how the algorithm works. And that's a good thing and a bad thing, because if you don't know what you're doing, you can have bad consequences. But if you have a good prior knowledge of your data, then this is a way to inject that prior knowledge into your algorithm. So you can also control it with the distance measure. You can control it with a distance measure. You can control it by the units you're measuring your features. You can choose to normalize them. The other thing is when we, instead of picking one nearest neighbor, we pick 5 nearest neighbors, 10 nearest neighbors. That's a hyperparameter. That is something that we can choose based on what works for us. That is one of the things. The other key thing is training versus testing. So essentially the procedure is that you have some training data where you have features and you have predictions. You want the algorithm to learn on these features and try to make these predictions. So when you do that, that's your training data. But now your model can really learn everything for that data, but it may not be good at learning for some new data. So for that, you so whatever label data you have, let's say you break it into 70 and 30%, or 60 or 40%. So now you have 40% data for which you have labels, and you have features, but your model hasn't seen that. So because your model hasn't seen that, when you run this test data through your model, and you get predictions, now you see how different are these predictions from what the actual values were. So let's say you had 100 homes. Now for 70 homes, you have figured out certain patterns, that if this house is smaller than this amount, smaller than the square footage, if this house is in this neighborhood and so on, it's likely that they won't be able to pay the mortgage. You've learned that for 70 homes, now you can predict that for 70 homes. But now there are 30 homes for which, as a trainer, you know the answer, but the model doesn't know. Now what your error is on those 30 is much more valuable. That's essentially the key, because the model hasn't seen these. Now once you get your errors on these 30, that's really what you're looking for. And if there's a huge difference between the training error and the test error, that means your model has probably overfit the data that you saw. So you want that distance to be less. So that's sort of the key thing. We'll keep touching that idea over and over again. Apart from that, yeah, it's just the efficiency. You can increase the efficiency using KD trees, increase the speed, and you can figure out other ways to do that. And sometimes it's just an approximate. If you use KD trees in such a way that you just go to one subset and you don't do any backtracking, that'll speed things up, but you won't always find the nearest neighbor. Sometimes you can also make it approximate to speed things up. That's the training error. So essentially, whenever you get a data set and you're building an algorithm for that, what you do is you break that set into 2 pieces. There is one piece, typically will be like 60 or 70% of data. You call that training data. And there's another piece which will be test data. Now your algorithm is trained on the training data. It never gets to see the test data. So you build your model and you predict on this training data and you measure the errors. So let's say for 70 homes, it made the prediction out of those. For 60 homes, it found correct predictions. So 60 out of 70 is your error. But it's possible that the model learns something very specific to these 70 points. If I give it another 100, it will be completely wrong. Or instead of 6 out of 7, it will be only 2 out of 7, something like that. So just because it has learned well on the training data means nothing.
So here when we learn data means let's say for the 70 part, so all of the 70% will be training, so it will all see those 70. So you're not using those any of the 70 for figuring out its error, right?
You do measure that, but
Yeah, I mean, if you have not linearized, then probably it is overfitting.
right,
If you wanted to direct it towards 0, then you have overfit, so most likely there will be a matching.
right.
Right. So, but
some training error, then on the other 30 you make the prediction again. If it is like 5 out of 7, then probably it's okay. If it's more like 2 out of 7, that means you most likely overfit the tool. So you need training error and you need test error. And test error is really what matters. Because making training error less is easy, you can just learn the data completely. But test is what the model hasn't seen. That is what really is valuable. Any other questions?
It's very interesting. I read about this afternoon, near scenario algorithm and bias and bias. Yeah, I just want to figure out. Yeah, very interesting to actually attend a lecture about this topic. And I studied.
Right.
So what slightly like efficiency here. So let us say you were taking grocery prices as an example where it's like this particular thing in whatever scenario. So typically speaking, let's say like Nashi food wanted to number by doing like square $3 to suggest each other, right? That would make easy, right? But if you want to feed in zip code as one of the region, right? Now it cannot be treated as a number. And my motivation for asking is that like maybe like a given house is very close to some other like known houses. So I just transfer to like one zip code, and thereby like house which is physically like farther may be a better representation because like this house is falling over that schooling zone, right? So how do you take that into account?
Say that again.
So if I could
So you're not worried about it's gonna have a bias towards the
right,
zip code, which, yeah, you'd hope for.
right,
Yeah.
It's okay. Google Maps takes all kinds of measures. They can take the attitude and the magnitude and
Oh, she's talking about latitude, longitude.
so that's right. That's even not like a good point, right? So that you can keep it there. But what I basically have is say like let's say all of us have houses, right? And I just stay very close to him, but like the zip code is like right here, and I fall in the same schooling zone as him, right? And he's really cheap because like oh sorry, like price here because like he's in like better schooling zone, right? So I'm basically physically closer to him, but he's in a better maybe region position. So how do you like feed in something like that? Zip code cannot be treated like a number really because like maybe again zip code also is like farther apart, like just because of numbers. Like what would be best way to like handle that?
so basically every house would have an address, and the address would return
Right.
I don't know what that is.
Geolocation.
The geolocation.
So
And
what
like
if
that.
you take the different zip codes and say that 0, 1, 2, 3, 4, 5. So they're like step clockwise basically. And for each step, so I remember this basically because this was one of the things in one of the videos. So in let's say there was a use case where you have to train a Unity and you had a feature which was an enum kind of a thing. So what they did was yeah, so they basically had if this is equal to so when we trained out right it was like the split points were if the it was not like greater than zero point 0.5 or less than zero point 0.5 kind of a thing, but it was equal to's, equal to and a mix of equal to's. so what you're saying is that like you may define one feature which is saying like zip code matches or not matches, and the value is either one which means same zip code or like zero which means a different zip code. And that's all you can use as like a normal answer. Is that
it's always part of the city, right? Does it ever cross cities? Because then it's almost like, well, you're still part of the city, and even though there's a zip code,
Yeah, so you don't give zip code in that sense, instead of giving zip code, you say X number of areas have,
right.
schooling area or not, and, whatever else, and then you basically enumerate all of
So
them.
if you can avoid zip code, it's okay, but then you could also say, we can use zip code to determine some other, who knows, like maybe the property taxes are based on zip code, maybe. Then you want to account for zip code as well, right?
Yes.
Something like that. But then you give more weightage to schooling district because then the prices are even higher.
So you basically use zip code to give property tax feature, and the other one is enumerated feature. So then you have.
Maybe sometimes we have to think about what does zip code really mean? And I think in ways we look at it, it has a lot to do with just delivering the mail, right? I mean, so compared to school districts